Okay, so let's get started. What am I doing? Um, so I apologize. I a little bit sick over the weekend, so my voice is different from usual. My mind is a little bit misty. So but I guess I have been teaching this for 4 to 5 years. So I guess even though I'm not in the best time in my mind, so I think I still can teach all right, okay, because I'm teaching game theory, so it shouldn't be a big issue. I've been doing game theory for years. So today we will be doing is finish the first topic of game theory, and then talk about some dynamics. The topic 5 will be done, and then we'll do topic 6, okay, and hopefully topic 6 with a lot of things to cover. But at least we will probably at least finish the subgame perfect equilibrium, dynamic games, and repeated game. I'm not sure we have time to finish, but we can touch some idea over that for today. So and the next assignment will be released because we've done chapter 5. So topic 5 and topic 4 will be one assignment. So let's get started. Very quickly, we review the basics of game theory. Then basically we have 4 main types. Of course, if you go further, you notice that game theory is way more complex than we do, but this is the standard topic that cover in most of the introductory micro classes. If you want to go further, there are lots, but I'm only able to cover the main 4 things. And I have mentioned today we are doing this, and then we end this topic, and then the next topic will be this one, subgame perfect equilibrium. So very importantly, because game theory is invented by mathematicians, so everything is very mathematical. And why we have to be mathematical, or we have to be very precise, is because of turn out the non-code game theory. You'll be very precise in the definition of how player plays, or how player can choose the action and what the outcomes. Otherwise, you can't define equilibrium precisely. So that means that even in your paper, you don't have to define things formally, but it should be evidence when you write down the game. It's very clear that who are the players, who are non-players, who are what each player can do, and what outcomes for all possible combination of action that are taken. So you cannot leave things undefined, which may not be the case when you have static games. But when you hold two dynamic games, which we'll talk about later, this class, then you may tend not to define everything, because you may think, okay, it's dominant, is something smart, is something stupid to do this in the first round. Then you don't define the game afterward, right? Then you are not allow us to check whether you're doing things right or wrong. Okay, it will be more clear later. But in the static game, I don't think you would have this issue, but it's very important to know you have to define 3 things. So just to remind you, it's very important to define who are the players and who are not players. That's very important. You have to make clear, because when you say who is the player, that means that those who are not player, then they cannot do anything besides maybe some function, right? For example, we talk about firms competition, and we will ignore consumer, right? I mean, sometimes, of course, you can include consumer as well, but if you ignore consumer, of course, they are still not a dummy, right? They are not just, you charge them 10 bucks, they will take 10 bucks, right? They respond to you, but you summarize the response in the demand function, right? Basically, you are making them a machine to response, but they're not allowed to choose. So this here means that they are what they're doing is cannot be choosing differently from what you program them to do. Okay, so player means that they can behave differently from what you program them to do, right? They can have life in their own, right? Just like imagine their NPC, right? The non-playable character, right? Just in the game, right? So they are not non-player means that they are not really behave, right? Of course, they can be very sophisticated, depending on the function you make, but they actually follow some standard rule as behaving. But players, they don't have to follow the rule. Okay, as long as they choose whatever action, they can interact. So it's very important. And strategy also have to be very careful in the sense that whether the set is discrete, whether this is continuous, whether you allow endpoints. Okay, and very often when you do financial decision, you allow zero or you allow infinity. Okay, and is it the set is finite? Closed is very important, because when it's not closed and bounded, then usually there's some issue about existence. So you have to be a little bit more careful about this. I mean, of course, this is important when you write your own game. Of course, if you apply the other games, then probably it's okay. But you will see this kind of issue there. And the payoff function is, again, an issue here is payoff function is saying that you have to tell whatever everyone might have done. You have to tell me how the payoff is. Okay. And if the discrete is not a problem, usually if every choice strategy space is discrete, right, you can just list them out as a matrix there. But when things are continuous, right, when the strategy is continuous, okay, is it your utility continuous in everyone's strategy? Okay. If not continuous, that's also an issue. Okay. Later you will see the existence of equilibrium. And very often you may think it's continuous, and everyone is not. Say auction is not continuous. Why? Because suppose you are not the highest bidder, right? You don't get suppose the first price auction, you don't get the object, right? No matter how much you bid, if you are below the highest, okay, you're not the highest winner. Suppose single object, right? And if you're the one of the highest, right, you might, depend on the rule, you may have chance to win it if by lottery, or depending on tie-breaking rule, you may not have any chance. But when you come from the highest, one of the highest, to you are the single highest epsilon more, right? You're the only highest, then you win the object, right? With positive utility. Suppose you win and the prize also win. That is discontinuous. And when this discontinuous, then there's a lot of things will happen. Equilibrium systems issue. There's a lot of things that goes on. So these things I'll mention later, but I just want to mention here now. The existence and how to write the game, I have to be very careful. Although in many daily application for your case, then probably it's not a big thing. But if you want to modify and write a simple game, then have to be very careful. So that there's a three things you have to define. I don't want to repeat. But we want to define strict dominance means if a strategy that is always worse off, no matter what other people are doing, we shouldn't take it, right? Because there's no reason to do it. And we see the present dilemma that the defect is dominance solvable, and turn out to be individual being not stupid, right? Can be stupid in the society, in the group sense, right? If they allowed it to sign contract, they would not end in DD, right? If there's a court that can enforce CC, right, they will do it, right? If I do C, if they do C, then it's possible, right? So that's why if you are aware of our department seminar, if people can write smart contract, they put a smart contract in this, you're allowed to get C, right? Because I can write contract that, okay, I will choose D if other people choose D. I will choose C if the other people choose C, right? And the contract can solve the equilibrium. So if you allow smart contract equilibrium, C can be the case, right? So it is possible that if you have some external way to enforce, C is possible, right? That's why the mafia and tri group, right? They have some external way to make sure that C would happen. Either they have violence, right? If you don't see, I kill your family, right? So that's why they would able to enforce C. Or if you do see, I'll take care of your family, right? Or there's some way to reward you to make sure C would happen, right? So that's why there's some collaboration, right? Even though police are able to separate them. So we can't catch all the criminal, right? Because of their way to make sure that C would happen, right? So that's why they can't, right? I think that's a very famous movie, I think, over in China, right? Called 投名状, right? So when you had to become a criminal organization, right? You have to commit a crime, right? So that if you defect, then we report the crime to police, then you have your 黑材料, right? The black evidence, right? So in the old days are the same, right? I mean, if you in the old days in the Asian China, right? If you do not corrupt, then you are not able to get a job in the civil servant, right? So you have to belong to the same group in the old days, right? And then you are not, if you defect, then they'll kill you, right? It's they have the very strong power in the village, in the same surname, right? I mean, or you come from the same group, right? You have to loyal to the group. So this is the kind of thing, right? Because everybody sees the defect, right? But they kill you, right? Or in the old days, Qing dynasty, right? If one guy make a mistake, right? They kill your whole family, right? If you make a mistake, they kill your friend, right? 连坐九族 is same idea, right? So you just try to make sure that you don't make this kind of mistake. So the next one is iterate dominance is applying the strict dominance, means that you keep deleting stillbirth strategy, right? But it's not easy, right? Because have to involve a lot of computation, right? But in the old days, maybe difficult to imagine. But now with AI or computation power, this might be possible, right? So that's why when you play chess online, we become boring. Why? Because everyone uses AI. A lot of people are cheating. So become no one make any stupid mistake. Then the chess become less interesting, right? And also playing online games, right? People use an illegal plugin, 外挂, right? Then you never make a stupid mistake. Then the game become less and less interesting, right? Because the game is more fun and then there's some human nature. But if machine versus machine, what are we playing against each other? Okay. So that is the idea, right? You keep deleting stupid strategy, right? And until there's one left over, then there's one prediction. This prediction is only a good one if you think 1 and 2 are smart enough. All right. If 1 and 2 are not smart enough, then this is not a good thing, right? You notice this one actually is stronger than Nash equilibrium. The requirement. Why? Because you require that I know you're smart and so on and so forth, right? I know you're smart, you know I'm smart, and I know you know I'm smart and so on and so forth, right? You need a lot of deep level. But what is required in Nash equilibrium, right, is you're here, If I want to deviate, that's not beneficial to do it. I don't need to think a lot, right? Here I have to be super smart, right? So, I mean, probably you can look at some paper talk about the epistemic foundation for the this solution concept, and you will see there's a lot of things behind, but it's beyond the scope of class talk about those. Next equilibrium, let's quickly review is if we are there, no one can change by changing on his own terms. Okay, there's no cooperation. So that's why there's the idea of what we call non-coded game theory, right? It's like everyone make decision on their own. Okay, is it the only way that people interact? No, right? But this is powerful enough that we focus on it. Okay, and in business, right? And this is a good model. Why? Because of antitrust policy, government regulation, firms are not allowed explicit colluding on, say, prices, right? They cannot say, we set the price as such, right? If you do it, then you go to jail, right? At least in the US or in Europe. And in China, they're slightly different, right? And then of course, in also other cases in US, you have some association can decide prices. Say labor union is the worker united together, right? Set the prices, then it's allowed, right? And China, there's a differently because of there's some cases the price is decided by the marketing reform committee, right? Or they have a price committee, so they're slightly different. But in general, in most of cases, business make their own decision. So so that's why this is a good model for business. Of course, there are other equilibrium concepts that allow firms to communicate. But next equilibrium is something the baseline, right? You would want at least the equilibrium would not be subject to individual deviation. No one would want to deviate, right? But if you say you allow people to communicate, then you will have a stronger equilibrium concept. So that's okay. We just strengthen it. You only need to strengthen it when you have more than one equilibrium, right? Otherwise, there's no point to strengthen it anyway. So when you have multiple equilibrium, we'll talk about that, right? So that would be something we can say more when we talk about alternative refinement. But at the moment, it's very simple. So that the existence is an issue, especially pure strategy may not exist because we know rock, paper, scissors doesn't exist as pure strategy, and you have to rely mix. And then multiple equilibrium, that is always there. But the problem, of course, is which one is, if you're multiple, what is your prediction? Okay. And then that's why I said we have to strengthen our equilibrium. Okay. That is getting stronger in concept there. And the last one is inefficiency. That means that the equilibrium is not efficient. That actually implies two things. One is if you are business application, you should able to design a game or introduce some new mechanism to improve it, right? If you're a firm owner, you see how the firm organized is not efficient, you should make it to behave more efficiently, right? So there's some way to do it because not efficient. Because if efficient, then nothing you can do further without harming one or the other, right? Or not efficient, then means that some bargaining can go on, or some design can go on. Okay, that is actually why economists is useful, right? Because it's not efficient, and economists can do something on it. Okay. So this is a classical model of Nash equilibrium is zero-sum game, right? And we know there's no pure strategy, next equilibrium, and at the end of last class, we talked about the mixed strategy equilibrium. Okay. And this is coordinate game, stack hunt game. Okay. And we know that the equilibrium would be this one and this one, right? Because this one player one don't want to deviate to here. That's not. Player two want to deviate here. No, because X is less than 10. So this is a nice equilibrium. Same, you can check for the hair and hair. Okay. Just to remind you that equilibrium is defined as strategy, not the payoff. Okay, it's a choice, not the number. Okay, so that's why I define a strategy, a strategy profile. So just to remind you that this you have multiple equilibrium, and here is what we say. If this is a firm, this is the value of manager or CEO. Okay, if the manager don't act, people may add in here. This is the manager or the CEO to move the company from 5-5 to 10-10. Okay, the internal conflict between each department, they can't work very well. That's why you need a CEO to coordinate what should be done. Why there's a strategic plan, right? That's to align everyone's interest there. Okay, so that is actually this is a main idea popular. I mean, as promoted by Roger Myerson. He keep talking about a political leader is trying to coordinate, right? You can imagine this is an old village, right, where the elderly, right, or the village head, why they can get money, right, why they can get political range, is because they can coordinate people, right? It is because of this, right? It's because of the guy who is able to say something, everyone want to listen, right? And he can lead to the better future of everyone. So that's the idea of why we need a political leader, right? As long as he charge, say, less than 10 units, people will listen to him. So in other words, it's coordinating game, which in this case is metric. So the next equilibrium can be either opera. Maybe I should just full screen, right? Otherwise, doesn't seem to be looking very good. So it's either opera or football. And as you can see, what is equilibrium? Because this is not one is better than others because they are not Pareto dominate. So what should be the outcome? What expect this outcome? What we expect? So can you predict what's the outcome? With opera or football, if you have to take. So what would be your prediction? If you don't know, let me give you a hint. It is why you cannot tell, because the model is do not tell you things that can affect decision, right? How we make decision is not just payoff, right? There's some other thing in the society that determine what it is. That's why they call focal point. And for example, suppose it's in Shandong. What we expect? It should be football, right? I guess, right? What would be happening in Shanghai? Right? Opera, right? Why? Why is the case? It's the gender, right? I think girl power is stronger in Shanghai compared to men, right? If you agree with me. And in Shandong, right, man power is stronger, right? As far as I know, I mean, I read the news is like I'm a little surprised because I just be one or twice to Shandong and they said, oh, women are not allowed to eat on the table, right? I mean, right? If you try to look at that, right? At least in some places still. But that means that I think football would be the one. I mean, I don't know that which one is better, but this is the hint, right? So anyway, I don't watch football. I don't watch opera anyway. So to me, I don't know which one is more attractive to me. But you can tell. The other one is anti-coordination game. And we know the equilibrium is either strict and chicken or chicken strict, right? Why? Because look at this one, you don't deviate, go down. This player two don't want to deviate to this one. Same symmetrically for the other guy. So what is a prediction? Okay, you have two equilibrium. What's prediction? Can you say anything? What is your take? If one and two are symmetric, the same gangster, probably you would not say anything, right? If I tell you, if gangster one is like 80 years old, gangster two is like 40 years old, what is your take? Who's going to chicken? The younger guy or the older guy? What do you think? Is the younger guy more brave or more crazy, or the older guy more brave, more crazy? Younger guy, right? The younger guy usually is more crazy, right? That's where you see the movie, right? The younger guy is like crazy. The older guy's okay. I mean, what's the point? Just lose face, right? It's better than die, right? So usually the younger, if you say one is younger guy, then I would think this is the outcome, right? So it really depends on how you think that guy is, right? And how the other side think the other guy is, right? Or you think this way: if the one is poor, much poor gangster, the guy number two is richer gangster, right? Then what you think, right? Then you would think the poor one have nothing to lose, then he must be more crazy, right? So this may happen, right? So that is how you try to solve the game. Except why I talk about this? Imagine this is a competition between two firms, right? And guy number one is the entrant, the guy number the incumbent, right? Then who is more crazy, right? So with limited liability, right? The new guy can just bankrupt, right? Very little to lose, right? So of course, the new entrant will just got crazy price, right? So what happened, right? In many cases in China, right, the new entrant come in, have a very low prices, right, to fight the new existing entrant, right? The reason is like this, right? The, the new guy don't want to fight. The existing guy don't want to fight, right? Because earning a lot already, right? If you fight them, probably lose a lot, right? Basically all die, right? Because this is like price war, right? But anyway, you can see this very important outside the game. Of course, I think Thomas Sealing, let's say Nobel Prize winner in the game theory as well, is that uh, he don't like this. I mean, although he's a focal point, but people don't really like it, and then because of you're saying something out of the game theory, right? If you say something out of game theory, you should define that, right? But I would say this is kind of reduced form idea, right? It's like we can also incorporate them into the model, and then you can work it out, right? Explicitly, right? You explicitly model how the guy like his life, right? how is benefit. I mean, you can model that, then you can figure out this unique equilibrium, right? Because the multiple equilibrium is because the model is not fully specify everything in detail, right? If you specify more detail, then you should have a unique equilibrium. Okay. I don't have a good take on this, whether it's the same as macro or econometrics, whether you want a reduced form model or you want a structural model. Okay. And both have benefit, right? And if this kind of reduced form, right, of course, things are more transparent, right? And of course, if you want to model them, how crazy the guys are, of course, you can do it, right? But it's up to you. And this is saying the Prisoner dilemma model it just deliver the same outcome as the strict dominance. Okay, and we define best response is the way that there's a best strategy, and then best correspondence is because we can have more than one strategy to respond to other players' choices, and we define best equilibrium. We write it as a mutual best response, right? Because it's everyone is best respond to each other, and that means a fixed point. Why we fixed point? This is to prove we can use a standard fixed point theorem for math to show existence of Nash equilibrium. And last time we actually go over this important example and how you draw a best response correspondence and figure out what is the Nash equilibrium. Of course, you can easily draw when you have two agents. When you're three, then you have to draw three-dimensional diagram. And you have four and more, probably can't draw that easily. But it is basically solving the system of equations. Need not be linear, but can be system of nonlinear equation. So it guarantee no solution can be any or more than one solution. So so that's why existence or uniqueness is one of the key when you solve Nash equilibrium. And I mentioned this already. I'm not going to talk too much about that. And then we talk about pure strategy. That's why we talk about mixed strategy. Okay. Here, mixed strategy is you talk about randomizing and a private device. So this probability is you just multiply because independent. Okay? And if you want, there's a device that everyone can see it. That is called correlated equilibrium by Altman in 1959. But we are not going to go to that direction. We just focus on this classical one. Is the everyone randomized like individual. Okay. And of course, this is more closer to what usually people do. Okay. And I used the big U to indicate this von Neumann-Morgenstern utility. And we go over this example last time, how we work it out, right? And only one dot point here. So now we are going to talk about this before the break, is to do it again, but we will show you this. Remember the battle of sex? It's opera and football as the two pure strategy Nash equilibrium, which you can check easily. And we want to show this is what happened? This is one more equilibrium. That's a mixed strategy equilibrium. Okay. And the question probably would be, the question is whether mixed strategy equilibrium makes sense. Okay. Later you will see. So again, because of two outcome, so mixed strategy over two action, two strategy would be very simple because you just need a run variable R1 minus R, right? and this Q 1 minus Q. Okay. So the expected payoff is very simple. It's RQ2, 1 minus Q, 1 minus R1, right? Because they do randomizing independently, right? So that is the important point, right? Otherwise, it would be actually more reasonable to say if they see today is Sunday, then they would do opera. If this is raining, they go to football. Actually, it's more efficient. Okay, look at the sky and do things. Although the sky condition is random, actually it's better. Okay, but we will not talk about that. We just focus on they randomize by themselves. If they randomize using the same device, we will actually can be better. Okay, but we focus on individual randomization. Okay, they call private device. So you can see this is the payoff. Remember, player 1 choose R, the girl. So just choose R to maximize this expected utility. You differentiate R, right? Would be 3Q minus 1. Okay. And whether this increasing, decreasing of 0 depends on Q, right? When Q is 1/3, then it's 0 doesn't mean matter your R. And more than 1/3, then positive, then you want to increase R as much as possible. That you choose 1, right? That's why it's 1, right? Because it's positive, then you go to the max. When Q is less than 1/3, then you want to be as low as possible, then you get 0. So here you can see why I said in the beginning, the strategy space is closed and bounded is very important, right? Otherwise, you will run into some problem. You will go to negative infinity, positive infinity, then you say some issue there. When Q is 1/3, doesn't matter. Okay, and you should expect something similar for other player. Okay, because of the fact that they're symmetric, and you will see something similar, and you will have that, which I'm not going to go line by line because I think you're a PhD student. So you solve actually 3 outcomes, but it's easier to see this graph, right? So player 1, less than 1/3. When Q is less than 1/3, then R is 0. Why? What does that mean? When Q less than 1/3 means that, let's look back here. What to try to make sense of this, right? From the game, okay? What does that mean? Q is the probability that the boy choose opera, right? If boy is not likely to choose opera, right? More likely to choose football, then the girl should choose football, right? So that means that R is 0. So that's why we have this guy, right? Whereas 1/3, it doesn't really matter what he's choosing, so we just go down here. When Q is more than 1/3, right? So is the boy has good probability to choose opera, and the girl like opera, so it's like this. So this should see this should make sense. Same white blue. When R is 0, which means that the girl is only choosing for football, of course the boy will choose football. Football means Q is 0, right? The probability putting on the opera is 0, right? And conversely, when R is with very large, right? Which means that it's more likely to be opera, then the boy would also choose opera as well, right? Although it's not his own taste, but better to be together or not together, right? Just here. And you have the straight line here, doesn't really matter. So you can see this 3 green dot will be the free equilibrium outcome. And probably you ask, is this reasonable? I don't know. It's hard to say. It's very fragile, this equilibrium, because of, I'm not sure if this is the boy and girl would do that, right? Of course, in those days, you don't have telephone, so maybe possible this would happen, right? Because if they are here or here, then actually one of them is very happy, but the other is not. Probably it's not going to be stable, but they may actually run this, right? But in this game, I'm not quite sure I would take the mixed strategy equilibrium. Okay, I would rather think this is this or this, and based on the other evidence, I would pick one of those as my prediction, because this is more like the equilibrium if they are fighting with each other. Okay? They're having Cold War, then maybe this is the case, but I would not think this is the outcome because it's unlikely to be true, right? Because there's some cases they go home, which I think that is not something I would expect to happen. That's why some people would think this is they should use a public random device, right? But we will not talk about those. So in this particular case, you will see the mixed strategy equilibrium. If they exist, you must imply this. Okay. If I is mixed over A and B, when you're mixing the two things, it must be the case that when I mix, they have same utility to me. Otherwise, why I'm mixing? I just pick the one that I like the most, right? When I'm randomizing, it must be the case that I'm indifferent. Okay. I mean, otherwise, if one is better than the other, why are you mixing, right? So the same idea is why when I do rock, paper, scissors, why I randomize between the free action is because the free action to me the same. If I know rock is always better, why I'm going to not choose rock, right? It must to me, if I choose rock, paper, and scissors, free of the action, have this some probability, with some positive probability that it must be same utility to me, right? And in the next strategy of equilibrium rock, paper, scissors, I'm randomizing. I don't care because Umemi doesn't care, right? But symmetrically, I also randomizing to make it also don't care. So that is the why equilibrium exists. It's because I don't care, right? Regardless of what you do it. Because, and same as what, because you're also randomizing, I also don't care what you do it. So it's a very weird concept, right? But still fix our idea of rock, paper, scissors, because we don't have, we different over the thing, okay? Okay, and that means that I can choose whatever. Okay, and I'm happy to randomize and make also the other guy also do the same. Okay, if I have particular taste over one or the other, then the equilibrium will break down. Okay? So this is kind of fragile, you can say, and that's why some people hate mixed strategy equilibrium. And probably you know the story of when John Nash talked to Van Neumann. Actually, he proved the existence of Nash equilibrium, and Van Neumann told Nash that, okay, this is just a fixed point field. Okay, without appreciate the importance. Of course, in some scenario, mixed strategy equilibrium is very natural. Okay, but in other cases, I'm not sure that going to mixed strategy equilibrium is the right way. I think you should try to think about the model more deeply. Okay, especially when you, unless you are something very special, rock paper scissors, I randomize because you randomize, right? Otherwise, I don't see particular point you randomize. Of course, randomization can mean that I do something, but the environment or there's some other random factor that makes things look like randomized. Okay, but can be considered a shortcut, right? So randomization can be considered as a reduced form of the modeling, right? If you want to really model the in the bigger detail, then probably it's not randomization. But anyway, I left you to decide whether randomize because even physics, right? People would think about quantum mechanics or macrophysics, right? Or microphysics, whether probability is a good thing or not. It's up to you to decide. I can't say it's more like personal taste. So I guess I end the point with this slide. It's a break. So consider case we have a finite players and finite strategy, okay, which means that you can draw a table, right? And that's what the very important result from Nash. Basically, he showed that in every finite game, there will be Nash equilibrium. Okay, that's very important because with that, we eventually can solve the game. Before him, there's no one prove it. Of course, as I said, when he sold to von Neumann, von Neumann said this is just a mathematical result without appreciating that this is actually opened up a lot of applications because once things exist, always exist in this kind of game, then you solve a lot of problems, right? Because you can do a lot of prediction. But of course, you want to ask what happened with the infinite game. There are also a result here, okay? But I'm not going into detail, but you can check when you really want to apply your model, you should check whether it exists an equilibrium, okay? But I think it's too technical for a class. I just leave it here, okay? So let's have a break of 15 minutes, and we'll come back for, we're almost done with this chapter. So we will be, after that, we'll talk about some application and then some refinement, and just the end, we talk about dynamic games, okay? So as usual, I leave you to, you reply if you want to do it. Of course, no force. Okay, if you want to say something, say something. If you don't want, it's okay. Okay? Just I want to know how fast or how well I'm doing. Okay? And for those who are late, just let you know that we're done with this chapter very soon, and then we will have a you will see the assignment. We'll resume at 10:40. It's a 15 minutes break. I see. So let's come back, see how well you are. Okay. Make sure it exists. Yes. Yeah, something of the game is very important. And whether you want to model it or not is your choice. But classical game theory don't model it, but nevertheless, I mean, it can be in your utility, right? Part of that. So it's okay. Can easily follow. Okay. It's more or less like a uniform distribution. So it's good. Surprisingly, I mean, as I said many times, in the undergrad, it's always like crazily like this. But I guess you're only first year, right? So not really into the crazy mood yet. If you ask your senior, then of course they think they are very tired and very busy. But now you're in honeymoon, I guess. Probably this is what you'll be told. This is what happened. It's a time in your grad school. Okay. And the question is, are you busy? Busy. B-U-S, right? Busyness, right? How busy you are. And it's like this. In the beginning, you're not very busy. And then with the end, you're very not so. And that means that your utility, how happy you are, look like this. And actually, every year is the best year compared to the future. Okay. Because you have less and less time. Now you're starting to have free time, you can explore around the coursework, but very soon next year you don't have time to explore. You have to focus on one particular topic, and you have less time. And research can be frustrating. Of course, it can be also very rewarding as well, but most of the time I suck up by the research, and your utility happiness actually go down each year. Of course, some of you may have different experience, maybe actually keep increasing, but that is on average looks like this. But hopefully, you know this as what I said is true. At the time you are in the grad school is like increasing more busy, and your utility is increasing dropping because you have to squeeze, because everyone have 24 hours, right? You have to squeeze something, sacrifice something to improve your research output. But anyway, you will know at the end of the day. Anyway, as long as you are in honeymoon, so I don't want to make that you feel miserable, but enjoy while lasts, right? Is 且行且正式, right? So let's give you an example where Maxwell equilibrium actually would make a lot of sense, and actually is the main point of this is to explain, especially for marketing, you will know very well. Price is not fixed, even for the same firm, over time. Right? For example, you look at the online website of the same good, right? It's not the same, even if you go to Tmall or Taobao, right? The same good, different seller, sell the same good at different prices, right? Or even the same good at different point of time will be different. And that drive variant, I think this former steel, I don't know, is the chief economist in Yahoo or Google or whatever. I mean, he has been in those places. And this is coming from his experience of buying a TV in the 80s, right? Those days, 80s is buying a TV is a big thing, right? And he figured out that why prices are different at different store and different time. He needs to shop around to look for a good bargain, right? So basically, this is the first model, or one of the first model to explain why prices are different, even for modular good, right? You don't expect this thing happen, right? But he come up with a model to explain why. And the model is very simple. So here, the simple is like N firm, because it's a store that sell TVs, right? And consumers continuum. So this is a trick. If you want things become smooth, then you assume continuum, then you avoid the problem of integer. So it doesn't change the things, but to make our life easier. And when you write the model, you usually assume continuum of consumer because consumer are not player, so it's okay. Because then you can describe them by demand function. So here, two type consumer. One of the type is informed, the other type is not. Okay. You can imagine informed are people who have very low search costs, right? Basically, they don't have too much time cost, or they are willing to search around. Uninformed are the consumer who have very high time cost or who are not sophisticated. Of course, there should be something in between, but you just make the model simple. I mean, you can extend the model to allow consumer with different costs of acquiring information, but that is a technical point anyway. So the sum of the two consumers is mass one, is normalization, doesn't mean anything here. Here, with the pay is V, same for all consumers. So consumer is the same, except the information cost. So to make the model simple, you can make it heterogeneous, but you will see this, make it simple. Here we have same good, so you should expect per chart competition, marginal cost C, right? You should see, okay, if only all the consumer informed it, you should expect marginal cost, right? As only equilibrium, right? If all consumer are informed it, right? Uninformed means later you will see is they only attach to one firm, not searching, not looking for other firm. And in that case, you should expect only monopoly price. Okay? But let's see what. So the firm we restrict to this. Why? Because this is only reasonable thing to think, right? Because no firm is charging below C, because it's charging C will be dominated anyway. Okay. So what's the profit here? The profit of each firm will be, this is the profit margin, okay, and times how many sales they can make. Okay. Here is if your price is not the lowest, okay, the minimum or the others, right? This means that if you're not the lowest in the market, you only get a equal share from uninformed. Okay. If you are one of the lowest, you get your own third, but you also get a share on those who are looking for bargain. Okay. So there are some die-hard friends for each firm. Okay. This is not contestable, right? It's something that stick to the firm no matter what price you're charging, as long as it's below V. And these are the consumer that is mobile. We just go to the place where charge lowest. If more than one lowest, they will equally share. So that will give you the graph like this. Okay. So everyone would have, one firm will have one of this, and this will be open to fight. Okay. And first, we try to argue that there are no pure search equilibrium. Okay? The argument is a little bit convoluted, but it's very elementary logic. So K is, remember K is number of firms that charge the lowest price. So if there are more than one firm charging the lower price, okay, so it means that two or more firm is trying to bottom. So consider three cases. If the lowest price is actually the V is high enough, okay, there are two firms, right? So it means that a firm, right? That means that everyone is charging the highest price, right? Then it means that one firm can reduce little and grab the whole market and basically benefit, right? So before it's one of them, but he will grab the whole market. So this cannot be the case, right? That can be equilibrium. And if this is medium price in the middle, still you can do the same, charge the existing highest price below a little bit and grab the whole market. Okay. But if it's already to the bottom, it's still not okay. Because the guy, one of the guy, because two guys, one of the guy that is actually the winner, actually not making any profit, right? Instead, he just go back to the highest price. He will get some profit from his own die-hard customer, right? Because this means the profit is zero, right? So if we go back to anything positive, then they make profit, right? So you can't have the case have two firms that charge the minimum. So now let's have only one firm charge the minimum. I don't know why of that. Or firm J charge the highest price possible. Okay. Well, because if you're only one firm, it's lowest price, of course the other firm will charge up to V, right? Because you're not winning anyway, right? So that must be the case. Now consider the case, one of the firm, the other did this firm, right? Is lowest, right? So the other firm actually charged the highest, but that will not be equilibrium because if the lowest, you want to keep increasing, right? But there's no way to stop. So unless you allow the price to be discrete, there will be nowhere to stop. Okay, there's always defect over there, right? So there's no possible combination of prices such that no one is going to deviate from that. There's always one more deviate. Is that okay? Now, by showing this means that no one is able to fix the price, right? If anyone fix the price, then anyone will change. So that's why he focused on mixed strategy equilibrium, and to make the model tractable, he focused on symmetric equilibrium, which means that everyone adopt the same strategy. Of course, you don't have to, but I just make it simple. And because everyone the same, I can describe the strategy by the CDF because of probability, right? And the infimum will be the lowest price, the super upper price, right? So that is the idea. Okay, and the small f, or is let was left. Okay, let f be the PDF. Now, how to prove this? I think of time, I'll quickly show you. You try to prove that maybe I just skip. Maybe I just quickly go over. So the idea is no one charge more than we. I think that's obvious. And there must be something charged near the lower price. Okay. There must be someone charged higher than low price. Otherwise, you can undercut them. So if there's lower bound, then there's an issue there. Okay. And there will be no mass, because if there's mass, then there will be high, and you undercut it a bit, you get better, because this is the way that the game is being designed. And at the maximum, okay, it's also charged at positive probability. Otherwise, you can improve, right? Because there's nothing there. Okay. And similarly, if there's a gap there, you can, if there's a gap there, you can, if you are below the gap, you actually can charge if there's some gap P1 and P2, no one charging, right? So there will be someone here, no one charged here, right? Then actually, why charge this point, right? Charge a little bit here is better, because you get a higher profit without violating. So anyway, if you don't want to bear with this detail, just saying that, okay, there exists some continuous equilibrium. And that would imply the following, okay? You have three equilibrium conditions that will characterize the equilibrium. First, the highest price is V, right? Which we have shown, because if there's no V is not the highest, you can always charge V to improve the payoff. And if you win, okay, if you win, you're the only winner, right? You win, you're the winner. You are charging lower price, you must be winning, right? You'll be winning, you win the whole market, right? Because the continuous is no mass. If you win at the lowest price, you must be the only one. Okay. And your winning will same as you are losing. To be indifferent. You must be indifferent compared to the highest price. So this is, remember, if you are doing mixed strategy, you're indifferent charging the lowest price and highest price, right? So this is payoff from the lowest price. This is payoff from the highest price, right? Remember the idea we said, mixed strategy, if you mix over things, you must be indifferent between them. Okay. This is the same. This is highest price. This is price between anything between lowest and highest. Okay. Why? Because if you any price P, okay, you will have your own die-hard customer, but you also have a chance to be one of the lowest. Okay. Because it depends on all other people charging, right? Because you're randomizing over others. So this is the probability that your price is less than other people. Suppose you're number two, your firm number one, then just P2, P3 up to P(n), right? And then independent, so just F1 minus F of P, right? Because they're higher than you. Should be you're the lowest, right? So the yes, it's less than or equal to, right? Okay. Because this is same as the probability that P2 is bigger than your P times probability that 3 bigger than your P, and so on and so forth, right? And each one will be realized as 1 minus F of P because they are all random using F as well, right? So this is probably that you are the lowest among all other firms, given you're charging P. Right? So this will fully categorize the set, right? So that means that you are able to solve this out with this equilibrium. Okay. So at least can show you that equilibrium exists and mixed strategy will make sense. And it has a good implication, right? Because it tells you mixed strategy indeed is used in business, right? Because at every point of time, right, firms are randomizing the price, giving discount or random good, right? So that they don't have to charge low price, right? So that's why implicitly they're colluding by mixed strategy, right? By setting the price, consumer doesn't know where to find the best price, right? And they don't have to compete to the lowest price. Even you can see in this standard model, homogeneous good for a child competition. But as long as consumer, some of the consumer is not searching, not everyone is searching. Only exists some consumer who are not willing to search, who are information constrained. Then if firms is doing mixed strategy, which is only possible case, then they're not making zero profit. Price is not marginal cost, right? So of course, if you go to zero, right, then of course everything boils down back, go back to the C, right? You can see you go to zero, the P will be equal to C, right? But if not, then it will deviate, right? So that's why if consumer are more information constrained, or the price is not very transparent, which is the case, then the price is more heterogeneous. Okay, so it does mean that when price is getting more complicated, right? This is the goal of the seller, right? The seller actually want to make the price very complicated, so that you don't understand why they price in this way, right? That's why you see a lot of websites, they make the pricing very complex, right? You can see why the airline, right, doesn't make the price very obvious, is to extract all the profit, right? And those of you who do operation management will know, right? That's how firms are making profit out of that. But anyway, now let's talk a little bit about beyond Nash, because when you have more than one equilibrium, then what can you do, right? First is you can use the very famous what we call Chamberlain refinement to remove Nash equilibrium with weakly dominant strategy, okay? Or sometimes you can call that they can do Pareto dominance. They focus on dominant strategy. Or if you allow them to sign contract, that is called strong equilibrium by Oppmann, 1959, I guess. And this is more recent one is called collision-proof Nash equilibrium. Is Descartes is 1984. Is they are not able to sign a binding contract, but they can talk. Okay? And once they talk, they are not able to sign contract, but means that things they can do must be credible. Okay. I recommend you to read those papers in order to understand how they're used, because they're highly technical. But it does mean that have some bites to some situations. And I guess the most useful one is in business is something we call players with basic optimal equilibrium. This is what we refer to do. As I said, in battle of sexes, we can focus on girl optimum or boy optimum, right? And that would actually fit in many situations, right? Or social norm or bargaining power that will favor one region over the others, right? So that would be the way that you want to optimize. Maybe you focus on, say, firm one optimal, or big firm optimal, or small firm optimal. So these are way to handle the problem. Okay. And the other, I mean, this is the easiest to do because I saw many times in business journal. And the above are more like game theory, which you may use it when you actually think this is not the best. And the other equilibrium concept is known as equilibrium that will be rationalizable. This epsilon equilibrium or collision equilibrium or collision proof equilibrium, I guess you can check these names, and there are many way more equilibrium over there. I don't want to mention one by one, but you can check those. But just try to give you some names, and you can check if you need. But I doubt you will need it at the moment. I guess it'll be okay. And one thing I want to mention, but I didn't put on the slides, which also will be something you may consider, is what we call evolutionary equilibrium. Okay, which is different from what we are saying, but instead of talking about agent choose equilibrium, you allow them. Players is not one player. Player, there will be many players because evolution, right? And they are doing strategy based on the hard code in the DNA, right? And those who winning, the DNA can survive and replicate, right? So that you will select a winning strategy. And evolution game theory is very popular in the 90s, but at the end of the day, it's not coming out as they expect because the prediction is not too much different from Nash equilibrium. It's some refinement, but I don't see there anything special because they actually at the end will pick some Nash equilibrium. So basically, you can imagine this is a way to refine your equilibrium, but not really producing anything new. Okay, but it probably also introduce some dynamics and sometimes you want to do it, but these days is not as popular. It's like more 80s or 90s people, early 2000 people use it. But it's still okay if you really want to, you think that evolutionary dynamics is something that you want to investigate. Okay. So let's end this quickly. There's a different kind of solution and there's different games we go over. And I hope you can use it. And because I can see this would be actually very useful because when we later you see when we talk about dynamic games, we will solve Nash equilibrium every round. Okay, so this is from the foundation of what we do after this set of slides. Okay, so I hope now you understand what's the Nash equilibrium, how to solve it. Okay, and now we actually go to the next set of slides, which is dynamic games. Okay, so I would say, at least for my own experience, I would say chapter, oh, not so thanks, sorry. I go too fast. Chapter 5 and chapter 6 is the thing that I use most of the time. So actually my research, most of my research is really rely on these two chapters. Of course, that means that there's a lot of things you can dig out from this one, even. And then, except you're doing some auction theory or some other complicated game. And I think these two chapters is the most people will do. Okay. So that's why I hope you know where how to solve these games. So let's focus. Let's look at motivation. Why timing is important. The static game is everyone make decision at the same time. And if everyone take time to make decision, okay, and that's we make different, right? Remember, we have a matching penny games is everyone sold their coin at the same time, right? If the coin is same, then player one wins. If I remember, this is the case. If the coin is same, player one lose. So player one won different side, and player two wins when they're the same. Okay. That means that if player two can see what player one do, right? Actually, player two is cheating, right? And player two would win for sure, right? And which means that player two can choose action based on what player one has chosen. Okay. So the strategy of player two is much more complicated. It's not an action, it's action conditional on or contingent on what player one has done. So the strategy in dynamic game is much more complicated. It's not just an action, but an action based on what other people have done. Okay, so it's more elaborate. That's why we have to talk about static before going dynamic. Or in general, it's what had been done so far. So that's why we call a depend on history. So history matters, right? As a Chinese student, you know history matters a lot, right? So history is a very important thing, right? We have 5,000 years of history, right? Everything is historical claim is very important. And so in this matching pennies game, player one can only choose head or tail, right? Because he can only show head or tail. But player two is more complicated. Player two, we have to choose if player one is head, what we do. If player two is tail, what we do, right? So it will be under head, he has to choose one of them, head or tail. Under tail, player two has to choose whether head or tail. So instead of two, it's four, right? It's contingent on what may have been done by player one. So that means that in order to define the game of extensive form or strategic or dynamic games can be very complicated. So of course, we don't define it this way, but it should be, everything should be found from your game description. So for example, you have to have this N, which is, we know very well, no problem. U is no problem as well, but later you see it's a little bit different. A, something we know already is S, or a kind of strategy, what can be done, okay? But these are a little bit different here. First is we have to define what is the set of strategy. Set of strategy is, later you define is what have been done, okay? But what's been done will be what other people have do, okay? The other thing is P, player function, is who can move at this point of time, okay? Because it's sequential move. Every time, it's just one guy is moving, okay? So it's mapping from what possible history, okay? What can happen except the last terminal nodes, except the last one. You point to a person, and based on history, we will define what is available at that point of time. And payoff will be based on the terminal notes, what is the payoff, okay? So this is easiest way to define. If you look at them, Max Collier, Winston, Green textbook, the definition is more complicated. The one I define is follow the Rubinstein and Osborne textbook definition. This is more concise, right? So because you need to define only history, player, action. This is a little bit, I guess you were not able to get it easily. So that's why we had good example. Okay. Strategy is, okay, will be in this case is for every history, what kind of action you can do, okay? So because the agent, a player, can act at many points in the history. So the strategy has to specify for all possible history, he can move. Okay. So this have to be very careful. Okay. The strategy is for all possible history that a player can move. Okay. An outcome is, of course, bunch of a collection of all the strategy, and Nash equilibrium can still define it this way. Okay. Nash equilibrium is still well defined. Now the problem is how do we define this NH? So let's see. Let me finish this example before we break. So very quickly. So two players showing the coin out. Player one go first, player two go second. Okay. History will be like this. At the time 0, no one have moved. So the history start from a null set or empty set. And player one can choose head or tail. Okay. So at that point, the history is either head or tail. And player two can choose head or tail afterward. Okay. If player one choose head, okay, the history is either HH or HT. If T is TH and TT. So because of this game terminate, these are all the terminal nodes. Okay. Do you look at that seller history is what have been done over the past, not just the last 4. Have to include all 3. So that's a set history. So this is the part that have to be a little bit more careful. Okay, this is the part that, but of course, later I'll show the game tree. This is very obvious. Okay, but this is when you write the math, that will be a little bit more trickier. Why? Because remember, player function is to tell you for any non-terminal history, which the first 3, you tell what are the player function. Okay, who can move. And the null history, player 1 move. And the history of H or tail, player 2 move. So this is player function. Okay. And that is what the set of available action. Under the history 0, player 1 can choose head or tail. Under H, player 1 can choose head or tail. Under tail, player 2 can also choose head or tail. So this is all available action. Okay. And payoff function is just what the payoff, right? Which is very simple because player 1 want to be different to win $1. If the same, he lose $1. So this is the outcome. Okay. So it looks very complicated, right? But everything, as we say, can be summarized by the tree diagram like this. Right? Here is a tree. Usually we draw from the top to the bottom or left to right. And the beginning is the beginning of history. So you start from a null history. Okay. And you can see the Note are the histories. Okay, this is history nothing. This history T, actually TH, right? This history X and H, this history XT, TH, TT, right? So everything is there, right? For every history, you tell who is moving. Player one is here, player two is here, player two is here, right? And these are all what action available at each point of time are the three branches. And the terminal nodes have hollow nodes, right? And the payoff are at the end. So everything is well defined from this tree. So tree, although looks simple, actually it includes everything we want to define the game. Okay, because you can find everything there, right? Just to remind you, your player set is here, right? Just collect everyone here, right? Next is history, or I already show it to you how to count them, right? Player function is also there. Action is also there, right? And strategy is also there, and also the payoff also there, right? So you can actually see everything's there, right? And NHAPU, right? 5 things. N H A P U. Okay. So once you have this, we can define strategy and outcomes. Okay. Since the time is over for the break, as a break first, we come back and tell you that you can see the strategy and outcomes are way more complicated. You can see at least them out is like humongous stuff. Okay, don't worry. We just need that from definition. When we actually solve it, we actually don't ever touch this thing. Okay, but this has to be very carefully defined. Otherwise, things would be not right. So let's resume at 11:40. So in case you haven't write down your you reply, you can still continue, or maybe I should. Maybe I should start a new you reply, just with one question in case you want to say something. Right? Maybe I should just end this guy, end the section, and then create only one thing if you want to say something. Anonymous for this time. So if you want to say something, say something. Okay? Say something. Yeah. So you say something, say something. If you don't, forget about it. Okay. We'll come back to define carefully the way you see Nash equilibrium is not sufficient. We will define what we call subgame perfect Nash equilibrium. And we will show you how backward induction is going to solve this game. Let's see 15 minutes later. So yeah, over. Eleven 42. Hi, welcome back. No one leave any message, so but let's quickly. So remember strategy. Strategy is to specify all possible time they can move, what they can do, right? So in this is very simple because everyone only move once, right? Player one only move when under history 0, and only choice is H and T. A player two has 2 history he can move, right? So that means that he has to specify what he can do in 2 different history. So that's why it's a Cartesian product of the 2 things. Okay. So it will be a strategy is not just 1 but 2. Okay. It will be HH, HT, TT, and TH. Since outcome we have 4 for player 2 and 2 to player 1, so you have 8 possible profile. And these are all the outcome, right? This is player 1 choose H. This is player 2 choose H. If player 1 choose H, player 2 choose H. If player 1 choose tail, so on and so forth, right? So you will have all this kind of stuff, okay? And so what you can check is, okay, remember the the simultaneous matching penny games. The only equilibrium is mixed strategy. If you forget what we said is here, right? Last time we figure out this only equilibrium is 1/2, 1/2, right? But in this game, I don't think there's a prediction. It's right? Because it's not a good one, right? Why? Because of I can see what you're doing, right? So that shouldn't be an issue. But of course, this is still can be the equilibrium here. Although we didn't show it, this can still be also equilibrium, right? Because I don't allow pure mixed strategy, but here actually can do mixed strategy. For player 1 and player 2 can also do mixed strategy. Okay? And in that case, everything is still a equilibrium, but I don't think it's reasonable, right? Why? Because you can see, right? If player 2 choose H here, player 2 choose T here, player 2 will sure win, right? This is why? Because player 2 get 1 is a -1, and 1 -1 here. So HT is dominant strategy, right? Other thing are dominated by this one, right? Dominant strategy. So you can't beat this one, right? So this is always the best. So you should expect this will happen. Okay. So we are trying to generalize this give you an example to see why what kind of solution we're getting. Okay. And this is called the prediction game. It's about entrant game. It's fit the business school very well. So there are 2 firms, new entrant and existing incumbent. There are 2 stages. In the first stage, the entrant decide whether in or out. If out, the game is over. If in, that was second stage. And in the second stage, once in, the incumbent decide to fight or accommodate, right? If whether to price war or let it in. If there's no entry, entrant don't cost a money, the incumbent still make $2. The market size is 2. And accommodate means that they peacefully beat the market is 1-1. But if they fight, then basically they lose all the money. It's more costly to entrance than incumbent, but you can make it -1-1 is also fine. doesn't really matter anyway. So you can rewrite this into a normal form, which is we do in last class. So we ignore the time. Okay, we can make it out is 0.2 to doesn't really matter the incumbent, right? And entrant when in, accommodate is 1.1, out is 3.1. Okay, so you can check there are two equilibrium here. First, this is a Nash equilibrium. Why? Player 1 don't want to deviate because C better than -3. Player 2 is indifferent, so this is Nash equilibrium. And this is also Nash equilibrium because player 1 don't want to go up and player 2 don't want to go left-hand side, right? Because 1 and -1. So these are two Nash equilibrium. Okay. But this out fights in is not something we believe. Why? Because I don't come in because I'm thinking if I come in, that will fight. But if actually I come in, it shouldn't be fighting because fighting is costly, right? Because fights, if I actually come in, fighting is actually -1, not fights 1, right? So there's no way I believe I come in that you would do a fight, right? So there's no way that this would happen, right? If you believe that, then yeah, it happened in many TV shows, right? A boy and girl fight, right? And the boy want to separate the girl, right? The girl said, if you go away, I jump out the window, right? But would he believe that, right? I don't know, but in some cases it does, or some it didn't, right? But that is the case, right? So it's not subgame perfect, right? So just like the standard case, right? If you the bad guy and the good guy, the bad guy take the hostage of innocent person, right? And tell the good guy, put down the gun, I'll release the hostage, right? Right? And the good guy will always believe that guy, right? Right or not, but you would not believe that, right? Because that is not subgame perfect, right? So that means that we can't use the old method to solve this. The time is important to say this is not a group prediction. So we have to take time into consideration. Okay, and time actually helps us to sharpen our prediction. Okay, it's not harming us. Indeed, it's helping us to reduce the number of prediction. Okay, because we have two equilibrium here, and later we will say only one is making sense. So basically, we're reducing the number of prediction by telling the time. People know more, and more information, actually more complex strategy, actually allow us to reduce the number of equilibrium, actually helping us, not harming us. Okay, so this case, how to solve this game is by using the famous method from dynamic programming, because we could focus on finite game, okay, finite period game. So we can always, there's a last stage here. Look at the last guy, what he would do. Okay, and look at incumbent, what he would do is looking at fight or accommodate. Accommodate is very better. So that's why this is the choice. This is never choice. Once I do it, the entrant would able to correctly predict that if this is in, he's either 1. It's out, is 0. So compare 0 to 1, he would choose in. Right? So this will be prediction of the model. That's called backward induction. Because you solve the game from the end stage and go backward. And you can see this is only solvable when the game has a finite stage, the final stage. But there's a game that's called infinite game, there's no finite stage. Then this method cannot be used. But as long as the game has finite stage, you can do it. Okay. And how to connect this principle of barrier reduction, and it's a contribution from Shelton in 1965. He would consider game by decomposing into subgame, which means that if I cut the tree, this is tree, we cut the tree from that point onward, itself is tree. What it's saying is subgame perfect equilibrium means that I look at every subtree. I require its component is also a Nash equilibrium in this subtree. Okay, so let's look at this again. Okay, this is a subgame. Okay, because itself is on tree. So I require us to solve a Nash equilibrium in this game, which is this one. And I require the whole game is also a Nash equilibrium. Okay, so that means that I would have two Nash equilibrium, but I have to include only this last one because those last one consistent with the subgame equilibrium. I'll give you more detail later, but this is the meaning. Okay. At the moment, maybe a little bit tricky. But let's look at this one first. Okay, ask yourself, what is strategy set for player 1 and player 2? How many subgame in this game? What is the set of SPEs? Okay, so I give you 2 minutes. You can try it because without trying, you never know. 2 minutes. Let me use this timer. Sorry. Don't look at the answer. The answer is in the book, either in the slide, but try to do it on your own. I go over it at the same time. Okay, time is over. So let me. So player 1 strategy set. It's very simple. You just only have A and B. Okay. Player 2 is more complicated. Player 2 is have two positive. So it will be C, D, E times F and G. Why? Because it will be, the strategy can be CF, CG, DF, DG, EF, EG, the 6. Okay, 6 total. So that's why I write the Cartesian product in this way. And the next will be how many subgames here? Subgame, as I define, can be game on its own. So game its own is you have player, you have everything well defined. So start from here. It's a game its own. You have starting point, you have end point, you have all the players, action, so on and so forth. One game. 2 as well. Over 3. Okay. Next is how to find subgame perfect equilibrium. We said barrel induction. Look at here. What is player 2 optimal strategy? There are 2, C or E. So these 2 are optimal. Look at 2, optimal is G. Okay. So look at pair 1. Pair 1, the choice depends on what 2 is doing. Okay. Suppose player 2 is doing CG. Under CG, player 1 actually can choose A, you get C, you get 1. You choose B, also get 1. Doesn't really matter. So we have ACG or BCG. They are both subgame perfect Nash equilibrium. Under EG, player 1 choose A, gets 0. Choose B, will get 1. So only B. So that's why you have 3 subgame perfect Nash equilibrium. Is that okay? This is something that the example will show, because I purposely get the example here because you need to know how to solve this game. Hundreds of games is very important. Okay, it's not easy to know by just listening, so that's why I put it there already here. So I explained already. Okay. So you may think subgame perfect is a good one. It's always good, but indeed, as we agree again, because there are many subgames, it's very difficult to go far ahead, right? Just like you play Go or play chess, it's very difficult to go to a lot of subgame to do calculation, right? So we make mistake. So this example of the process, okay? So here is the game. In each period, there will be $2 generate, okay? So initially you start with $4, okay? And the one who calls stop will get $2 more than the other guy. So if player 1 calls stop, the player 1 got $3. The other one got 1 because $4, the other guy got $2 more. And if player 1 continues, player 2 call stop, player 1 get 1, player 2 get 2, player 4 get 4, because now it becomes $6, right? Because total is 4, now it's 6. There's 8, there is 10, there is 12, and there is I don't know, whatever, 14, right? So every time, if the one who calls stop, we get $2 more. Okay. And maybe this will be 6A. No, this is right. Sorry. Where do you call it? Yeah, that's right. And this contour doesn't matter anyway. Okay. So because N already, okay. So what is the subgame perfectness equilibrium? Look at this one. It doesn't really matter because the same. So just the same. And this player one is moving. Player one will choose this guy, right? And player two, he know if he stop, he'll get 6. If continue, get 5. So he's stop. And player one, look at this, is he continue, you get 4. Otherwise, you get 5. He will just stop here, right? So everyone would choose stop, correct? And that actually is the Pareto inefficient one, right? If everyone wait until the end, everyone is at least better than 3-1, right? In how many sub-game, right? This is 1 sub-game, 2 sub-game, 3 sub-game, 4 sub-game, 5 sub-game, 6 sub-game. The how 6 sub-game comes in. Okay. And the question is this prediction reasonable? Right? The worst case, probably ask, if you go to the lab, what do you see? Okay, actually humans are not that stupid. Turn out most they, I think, remember is something like somewhat here. Okay. Of course, there's some people grab this thing, but most likely people have to try to be here. Not all to the end, but they stop somewhere. But at least it's not this one, nor this one. Okay. But there are some people just grab in the beginning because people are very smart. But not everyone is very smart. They will just wait. Actually, if you're not very smart, actually better. If you're too smart, then actually worse, right? If both of you are very smart, then I just like harm each other, right? You just like what they said, right? It's 卷，大家卷起来就 everyone got harmed. So the next is I want to introduce something, but I don't want to talk about the definition because I don't think we care that much. So far, we talk about the case where agent, the player move sequentially, one guy, another. But usually we allow it to be more complicated. We can allow with simultaneous move. So there can be more than one player move at the same time. So this is the game that we use most often, right? Because that means that firm will compete in different stages, right? Maybe first firm compete in building the capacity or R&D, and then firm compete in the product market, right? Or the supply chain, first the game between the supplier, second stage between the retailer, right? So that's very common, this thing is being done. So I would say this game is one of the most frequently observed in all the journals when we talk about apply. So definition, that's why it's very clear. It's not different from before. Same. What different is this guy. Okay. Is the player function is no longer mapped to n, but now is to the power n. It's the power set. Means you map to a subset of players. You can tell you not just one move and bunch of guys moving. An action will be a product set, right? Just like who can be moving, not just one guy. Other thing the same. So you can see not much different, right? In terms of definition. And in terms of game tree, it's also very simple. But let's see this example again. And this incorporate the simultaneous matching tennis games. Now they move together. the history is only this guy. Okay, there's no H and T, it's gone. Right? Because two players are moved together. Right? There's one stage, they move together. Okay. And the player function will be mapping from empty history to 1 and 2 because you don't need to, they are terminal, right? So you only need to, player function only to non-terminal one. The action set is just what they can do, right? But you product of them, so there's the actions like this. And the payoff is just same as before. Okay. So this is easy when they only one stage, but more than one stage, it's a bit more complicated. So we have to define one thing we call information set. So this is the most tricky part in this chapter, is to define who know where they are. Okay. Whether you know where you are is very important. And this set will tell us whether it's a we can define a subgame or not. The subgame cannot cut through the information set. So let's see how we define it. So we will define information set in here based on they move together. So when we draw a tree diagram with the information set like this, we will imply that the player 1, the player 2, does not know where he is. He doesn't know player 1 has chosen head or tail. In that case, he is not allowed to choose H and T here. He can only choose H or T. Okay, there's no way he can choose differently in different branches. So this limits who can be done because he doesn't know where he is. Okay, so that is very important. And that means there's only one subgame because you cannot cut through this. So simultaneous move basically make that your subgame more strict, okay? And you solve the game and same. So I will leave this to you for your small homework. Not homework, but we'll talk about this in the next class. How to define this strategy set of 1 and 2, and how much of games are there. Okay. After that, we define it. There's some example, and then we'll do with the game. Okay. So basically, we finished almost everything we want to finish, but with some applications have not done. But otherwise, we are on the schedule as we expect. Okay. So I will see you next week. Enjoy the holiday on next Wednesday. Next Wednesday holiday. I don't know whether you know. It's hiking holiday. So 重阳节9月9日依山东兄弟 if you know. So I see you next. Enjoy the hiking.